let's explore the principles of cohomology required for the H-phi formulation to impose current sources. So we will define a phi formulation, and we will see how to set up current sources and what are the technicalities that come with that. So let's draw a simple geometry with, as usual, a donut. Top of this donut, we'll add a box. The purpose of this box is to split the donut into the left and right piece so that we can easily access the circulation loop around on both sides of the donut. Now let's add a cylinder that will be used as a supply, current supply wire. And let's also add the final air box around. Now we can request a fragment all operation to do all the Boolean operations and do all the fragmenting between all the shapes. Now that it's done, we can access each piece separately. And to keep the geometry simple, we will do a few unions. So we will group all the non-conducting regions. And we will also hide these regions now to access what's inside. These are also two non-conducting regions. And now we can apply that and build that so we can see and pick for the next operation. All right, now we can add another union, again just for convenience, where we will group all the pieces of the donut that are on the left side. We can apply, build until, and then the last union for convenience on the right side. We will also group these three pieces. So the purpose of all this is to get a geometry such that we can play around with the circulation loops around the donut. So this is done. We can confirm the changes. And now we can easily define our materials. So we will use air as a non-conductor here on the region that we unioned. Then we will also say that the conductor is made out of aluminum. And because we made a union at the geometry CAD level, now this is very easy to pick. So that's done. And now we can move on to the phi-physics definition. So we could use H-phi, for example, to see how an AC current flows. But here, for this video, we'll only explore the phi formulation. Please refer to other videos for the H-phi formulation. So we will add, so we will do a steady state simulation, so a static current flow, and we will only compute the magnetic field in the non-conducting region. The conductor part will not be included in the physics. It will not even have any unknown associated to it. We will only take into account the effect of the current flowing on the magnetic field in the air around. So this phi formulation really allows to get the magnetic field in the non-conducting region without even simulating the current flow in the conductors. So let's do this. So first, well, the phi-physics is only defined in the air. And then we will add these current sources. So now we can hide the air. And the way we will define the current sources is a bit more technical or the H-phi formulation compared to, for example, the AV formulation, we'll define it by providing circulations around the conductor. So we could say that we have 1 amp static current flowing, and we have to provide a closed loop to say where it's flowing. We select this closed loop. Now you see arrows appearing. Now you use your right hand, and this will determine that the current actually is flowing to the right side from this circulation. Now, based on the topology of this donut, this is not enough because it's still undefined how much current flows in or flows out or flows in the other side of the donut. Now we have to make a decision based on what we know. You might know how much current flows in and how much current flows on the left side. Now here, again, this is just an illustration example. It might be you don't have access to these quantities. But what we could do, for example, to have a fully determined system where all the quantities are set, is to define another current source where we'll say that we have also 1 amp flowing, and then we have to pick another curve here. We have 1 amp flowing here. So if we work like this, then with the right hand side rule, we have 1 amp flowing to the right on that circulation loop, and we have 1 amp flowing to the left on the other one because of the orientation of the arrows shown. So this means the current will loop around the donut, and the net current flowing in will be 0 because it's exactly compensated how much current flows on this loop, and on this loop perfectly compensates, and you will therefore have 0 amp flowing in. If you would not have 1 amp here, if you would have, for example, 2 amp, then this means that there would be 1 amp flowing out from the left conductor, and also, of course, 1 amp flowing in from the right input cylindrical conductor. So you can really define, based on circulation, how much current, total current flows at each part of your geometry, and the amount of equations that you have to provide is equal to the, well, it's entirely defined by the topology of your geometry. If you have 1 conductor flowing in air, then you just need 1 circulation because you entirely define the system with only 1 equation. In this case, if you think physically, you will realize that you need 2 constraints so that all the currents everywhere are properly defined. Now this simulation, we can run it. So let's define a simulation. And we could use the mesh refiner in expert setting, and we could say that we have let's say 0.2 scale factor. We could do 0.5 here because we don't have induced current, so this will be accurate enough. And then we can click the mesh button. Now we will request output. So what do we want to see? We could want to see the magnetic field be in Teslas, for example, and we want to see it where? We want to see it in the air. Now, of course, at any time, as usual in Allsolve, you can access the script that has been automatically generated, and you'll see that it's really simple. Although it involves a lot of mathematical complexity, you end up with a less than 50 lines of code script. And this is fully ready for domain decomposition acceleration and running it for a very fine mesh on the cloud. Now the mesh is finished. We could visualize it. And as you can see, it has been refined where needed. Now we can run it. So we could use 1 node with 1 core. It's not a heavy simulation, so we can just go with that. Now the simulation is finished running. We can check the logs. We can see that it took 900 milliseconds to solve, and we can download the results. Now, what do we expect as results? we can for that go back to the current source simulation. So we do expect, based on 1 amp flowing there and 1 amp flowing from the right to left there, we do expect to have a magnetic field that goes from the outside inside of the donut. And this is exactly what we will see in the visualization. So let's download it. We can see that it's very weak because it's a very small current and a very large donut of around 1 meter. But the magnetic intensity looks correct. And now we can also visualize the glyphs of it. Make a cut to see how they're pointing. And indeed, the magnetic field goes from the outside, from the top to the bottom, as expected.